Welcome back to my lecture series on James space, a counterexample in functional analysis and more precisely Banach space theory. In the last lecture, we finished the chapter on Schauder bases, and we will, in this chapter now, which I hope to complete in this one video, develop some theorems about isomorphisms for Banach spaces, which are kind of like C0 in the sense that they have a monotone and shrinking basis. So let's jump right in. Isomorphisms. Okay, we will begin with a rather trivial proposition. Now, since when we have a Banach space with a basis, every vector has a representation like this. So a vector A might look like this. Nothing seems more natural than to identify this A with this unique sequence of scalars. And that's exactly what we are going to do in this proposition. So let X with some norm be a Banach space. With a basis xn. Then we define S, and we define it regarding X as the set of all the scalar sequences such that this sum right here converges. And we will also define a norm for this space. So we have a sequence in here. And we will define this simply to be the norm of the vector that we get when we put this sequence into this convergent series. Okay, and now the statement is that this space with this norm is a Banach space and the following map psi from X to S, which maps any vector which has such a representation simply to this coordinate sequence. This psi is an isometric isomorphism. And for the proof, I think it is okay to say that it is obvious that S with this norm is a normed K vector space. You can check that yourself. Now, let A and B be vectors from X, and they shall be different. Well, then A has a representation like this, and B has a representation like this, with some sequences alpha and beta. And because this representation is unique, it quickly follows that alpha n is not the same as beta n, and thus that psi A is not the same as psi B. So this is injective, and to show that it is surjective, let's now take any sequence from S. Then we just define A to be this sequence which converges because alpha n is in the set, that's just per definition. Then psi of A is simply alpha n, right? So this is surjective and psi is an isomorphism. And for the isometry, we just check this, the norm of our vector A, which is the norm of this. This is the same as the norm of alpha n, the S norm of alpha n, and thus this is the same as the S norm of psi of A. So this is also an isometry. And because this is an isometric isomorphism, it also follows that S must be necessarily complete. And we are done with the proof. So this was rather easy and uninteresting, but it will get interesting now when we define a similar space for the double dual space of X. We can define this space for any Banach space with a basis. However, the isometric isomorphism is only achieved when the basis is monotone and shrinking. Now I want to make a quick remark about notation. Now, since we identify X with a space S of X, we might be inclined to identify our double dual space with a space Sx dash dash. However, we want to make a different identification for x dash dash. And because we make a different identification, I will write S dash dash of x. And because I want to abridge this notation even further, I will call Sx only S, as we already did above. And I will call this S dash dash. However, and this is now important to note, this is not S's double dual. Okay? This is a notation for a space that we will identify x dash dash with. But it's not really related to this at first. We will get to that later. And we will now get to our lemma where we will introduce this space. So again, let X be a Banach space, and Xn a basis for that Banach space. Then we define S dash dash with regards to X as the following set. We will again take sequences of scalars, but now we want the supremum of the norms of these partial representations that we get from this sequence. We want this to be finite. And as you may have guessed now, we will define a norm on this space as such. This shall be the supremum that we also wrote up there. Okay. And now the statement of our lemma is that then S dash dash with this new norm is a Banach space. All right. No isomorphism for now, only Banach space. So for the proof, I will again note that it is obviously true that S dash dash with this norm is a normed K vector space. So this is a normed space. Now, to show that this is complete, we will take a Cauchy sequence. Now this will be a sequence of sequences. So we will have a double index, and this is a sequence in the index n, but it is the jth sequence. So this is now a sequence in S dash dash, a sequence of sequences. And not just any sequence. This is a Cauchy sequence with regards to this new norm. Cauchy sequence. Now we take J and J dash as, I will call it, outer indices, and we will fix an m which is greater or equal to 0 as an inner index. Then difference of alpha mj and alpha mj dash. We will now find a inequality for this. This is the same as the inverse of the norm of the mth basis vector times this. So we just multiplied a 1. Now this is the same as the inverse of this norm times the following. We will do the same trick that we already did earlier. We will add some dimensions and then remove some dimensions again. Here, this is the minus. And we do this to apply now the triangle inequality. And when we do that, well, we get norm dashes here and brackets here. And then we can find an inequality with the supremum. So this is less than or equal to 2 times, we keep this factor, times the supremum of these vectors here. And well, this is just 2 times this factor times the norm of what? Of these sequences in the S dash dash norm. And we will find similarly for m equals 1 that the difference of alpha 1j minus alpha 1j dash is less than the inverse norm of x1 times this norm of the difference of these sequences. And here we don't need to use the 2. This is a trick that we used a lot already, so I will not go over it. And now, since this is a Cauchy sequence, we can conclude that these differences will go to 0 as j and j dash get bigger and bigger. So we get that alpha mj minus alpha mj dash goes to 0 as j and j dash go to infinity. Okay. So for fixed inner index m, we have that this sequence right here, now in J, is a Cauchy sequence of scalars. So this is K Cauchy. And thus it converges, and we can denote a limit alpha n in the following way. Nice. And now we want to show that actually this Cauchy sequence alpha nj converges to the sequence of these limits. And for that we will consider an epsilon greater than 0, and we want to have a j, capital J, in the natural numbers such that for all j and j dash which are greater than j or equal to j, we have that the difference of alpha nj minus alpha nj dash in the S dash dash norm, this shall be less than epsilon. We can just do that because it's a Cauchy sequence. And with letting j dash tend to infinity, we get that for all m in the natural numbers and for all j which are greater or equal to capital J, the norm of this vector here, this is less than or equal to epsilon. And thus we can conclude that for all j greater than capital J, the supremum over these is less than or equal to epsilon. So the norm of alpha n j minus alpha n in the S dash dash norm is less than or equal to 0. And what does this tell us? This does tell us that this sequence converges to that one. And we are done. We now know that S dash dash with this norm is complete. It's a Banach space. And now we get to the central theorem of this chapter, in which we will finally apply the properties of monotone and shrinking bases. So, theorem 2.3. Now, X shall again be a Banach space, and Xn a monotone and shrinking basis for X. Now, let S dash dash be the space from the preceding lemma 2.2, and as always, let Xn dash be the coordinate functionals. Okay, now we define phi going from the double dual space of X to S dash dash, which is not the double dual space of S, mind you. In the following way, we map any functional to the sequence that we get when we put the coordinate functionals into this functional. Now, this is a sequence with index n. And the statement is that phi is an isometric isomorphism, isom. So for the proof, and this will be one hell of a proof, we will first note that since Xn is shrinking, we know from theorem 1.18 that the coordinate functionals form a basis of the dual space. And we also know that the basic constant of these coordinate functionals is less than or equal to that of our base Xn. And since Xn is monotone, its basic constant is 1. However, a basic constant is always greater or equal to 1. So, the Xn dashs also have basic constant 1 and are thus monotone. Also, the Xn dashs are monotone. Now, for all functionals from the double dual space and all functionals from the regular dual space and a natural number m, we get that the absolute value of x dash applied to the following functional, the following vector, not a functional, sorry. This is the same per linearity as the absolute value of this sum right here. So these and these, they are just regular numbers. And this is the same as applying x dash dash to, and now it actually is a functional, And now we just use the following property of the norm. So this is less than or equal to this product right here. And we know from theorem 1.18 that this converges to x dash, right? This was exactly the representation of a functional. So this is less than or equal to the norm of x dash dash times the norm of x dash. This inequality just comes from the fact that the basis constant is 1. So we know that this is less than or equal to 1 times, and then we get here the infinite sum, and so on. You get the idea. Let's give this a name very quickly, 2.1, and move on. Now if we have that this sum right here is not 0, then per Hahn-Banach there exists a functional x dash with norm 1 such that x dash applied to this sum, which is a vector, so x dash applied to this vector is just the norm of this vector. And then with 2.1, so the inequality that we just got, it follows that the norm of this sum is less than or equal to the norm of x dash dash. Okay. And this inequality is also trivial for the trivial 0 case. For the 0 case, since then this functional already has to be 0. It's trivial. And thus we get that when we apply our soon-to-be isomorphism to x dash dash and look at the norm, where this is the same as the norm of this sequence right here, and this is the same as the supremum over all these terms, well, this must be less than or equal to the norm of x dash dash. And we will also give this a name, 2.2, because as you might see, this is one direction of isometry, right? If we get another inequality this way, then we have isometry. And this also shows us that this is actually well defined in the sense that phi of x dash dash is actually an element of s dash dash. And clearly, phi is linear. This is clear. And further, phi is injective, and I will show that real quick. So if we have x dash dash from our double dual space with phi of x dash dash being equal to 0, we have that x dash dash applied to any functional, where this is just the same as applying x dash dash to this representation of the functional, which looks like this. Per linearity, this is the same as this. And this is then 0, because this is exactly the sequence that we chose to be 0. And thus, x dash dash must be 0. So phi has a trivial kernel, and thus it is injective. And what is left to show is that it is surjective and that it is an isometry. So to show that it is surjective, we take any sequence in our space S dash dash. And we also take some functional from our dual space, and we take positive integers such that m1 is less than m2. Then we can conclude that the sum from m1 plus 1 up to m2 of alpha n times x dash applied to the basis vectors, this in the absolute value, that this, which is the same as x dash applied to this vector, is less than or equal to the norm, the m norm, which you may remember from last video, of the functional times the norm of this vector. Now we use the same trick that we already used so much. We will just break this sum up and then use the triangle inequality. So this is less than the norm of x dash dash, the m norm, of the following. First we have the norm of the vector up to m2 dimensions, and then the norm of the vector only up to m1 dimensions. And this is less than or equal to then the supremum if we let the maximum dimension here in these terms be variable. If we then take the supremum, that's of course bigger or equal, and that's exactly the s dash dash norm. So this is less than or equal to 2 times m norm of x dash times the norm of alpha n from s dash dash. And what's so important about this is that since xn is a shrinking basis, this converges to 0 because xn is shrinking. That's the definition of shrinking, that this right here goes to 0, and thus it all goes to 0. Thus this sum right here makes sense because it converges. And what we will now show is that this functional x0 dash dash, which maps any functional to this sum, that this is the Ur-functional. So we want to show that phi of x0 dash dash is actually just alpha n. This we will show now. So I will cross it out for now. And again, I think that it is obvious that this functional is actually linear. So for x dash a functional and m a natural number, we have that the absolute value of this sum right here is less than or equal to the norm of x dash times the norm of our vector alpha n xn. This is less than or equal to x dash times the norm of alpha n in the s dash dash norm, and thus the absolute value of x0 dash dash applied to x dash is less than or equal to the norm of x dash times the s dash dash norm of alpha n for all functionals. So the functional that we just defined is actually a continuous linear functional from the double dual space. And we have that phi of x0 dash dash, which was defined as the following sequence. This is just the same as when we take the infinite sum. We will use a j here for the index. Alpha j xn dash, so the nth coordinate functional, applied to xj, and then this whole thing has index n. This is just alpha n because of the properties that happen right here with the coordinate functionals. So phi is an isomorphism. Now, for all x dash and x dash dash from these corresponding spaces, we have that x dash dash applied to x dash, well, this is just the same as x dash dash applied to this representation of our functional. And this is less than or equal to the norm of x dash times the norm of x dash dash xn dash xn per linearity, and then the inequality of the multiplicative inequality of the norm. And this is less than or equal to the norm of x dash times the norm of x dash dash xn dash, so of this sequence in the s dash dash norm, and well, this is just the same as the norm of x dash times the norm of phi of x dash dash. And if we give this a name, we can in a nice way write the following, that from 2.2 plus 2.3 it follows that phi is an isometry. So it's an isometric isomorphism, isom. We conclude our proof, and that is it already for this chapter. That's everything that we need. So in the next video, we can finally start talking about our beloved James space. So we have our space X. We have also our space X dash and our space X dash dash. So dual space and double dual space. And we identify them in the following way. We identify X with S of X, and we identify X dash with S dash of X, which I have not gone over now, but this is actually the same identification that we use for the regular space. So this is just actually S of X dash. And we also identify X dash dash with S dash dash of X. If we have a space with a monotone and shrinking basis, only then this is possible in this way. And the nice thing is that this space and this space have the same norm. And this will allow us to embed X into X dash dash. And you may have noticed that S, so Sx, contains sequences, contains alpha n's, such that this sum right here converges. So n1 to infinity. This converges. And that S dash dash contains alpha n's such that well, the sequence of partial series, of partial sums, that this is bounded. And this has some striking similarities to well-known spaces, such as, who would have thought, C0 and L infinity. And indeed, what we have just done in this chapter is a generalization of the identifications that we get for C0. So SC0 is actually just C0, and S dash of C0, this is just L1, and S dash dash of C0 is actually just L infinity. Now, that was a quick remark, and I hope to see you in the next video where we will finally engage in the study of James space. Bye bye.